Hello viewers, welcome to video number 97 of the channel MALACHEMPHILIC, and video number 97 is the 38th episode of Chemical Thermodynamics. Topic of this episode is entropy changes in reversible non-cyclic processes. So let's start. Reversible process already I have discussed in my previous videos. Link of the playlist is given in the description box. So reversible process, in very brief, let me tell you, this process occurs through a large number of infinitesimally small steps, and naturally this process is imaginary. Practically it cannot be performed. Now coming to the entropy change. Entropy change delta S, which is denoted by delta S, of the system, that formula is Q by T. What is Q? Q is the heat absorbed or released divided by this temperature at which this heat exchange occurs. Now, in my earlier videos, I have shown you that this formula is derived from Carnot cycle, where all the steps are reversible. So we can write it as here Q reversible by T. And in this equation, when we apply this equation, when temperature is constant. Okay. Now another way we can represent delta S system, that is equal to summation of all the small steps. Okay, change of entropy in each small steps, and that is equal to del Q reversible by T. So this equation, this formula, that is applicable in any situation whether temperature is constant or not, because these small changes of entropy, that means in reversible process, we know that between any two steps equilibrium is maintained, and then between any two consecutive steps this temperature is constant. But each step temperature is constant, but from one step to other it may vary. So therefore here we cannot write temperature is constant when the temperature is not constant or constant, whatever it is. Then we can use this equation. ds, integration of ds is equal to del Q reversible by T. And that is equal to, here overall you can write it as, that is equal to your Q reversible by T. Okay, Q reversible by T when this temperature is coming constant, right? Now coming to the entropy change in reversible process. Here entropy change, we mean the entropy change of the system as well as entropy change of the surroundings. Now try to understand. Say this is my system and this is surrounding. Process is reversible. Reversible means equilibrium is maintained in each step. System and surrounding is in equilibrium, and both are having same temperature T, under constant temperature T. Okay. Now, small amount of heat is transferred from surrounding to system. Say that is del Q. Okay, and it is a reversible process. You can write del Q reversible. Right. Then, entropy change of this system. What is the entropy change of the system? Delta S system, that will be is equal to plus Q overall. This is overall I am writing. So, plus Q reversible, or if you want to write this way, integration of ds plus ds, that is not plus, ds, that is equal to your del Q reversible by T. Okay, and this we can write it as your Q overall, that is Q reversible by T. So, delta S system, as we know, we can write it as plus Q reversible by T. In the reversible process, this small amount of heat is absorbed by the system from the surrounding, and we have represented that equation, means that changes, and this is this one. Now, surrounding releases del Q, or overall if I write Q reversible amount of heat. So, therefore, delta S surroundings, that will be is equal to minus, it is releases, that means minus. So, minus Q reversible of system, so in terms of system, minus Q reversible divided by T. So, what is the total entropy change? So, delta S total is equal to, which we call it as delta S universe, is equal to delta S system plus delta S surroundings. Okay, that is equal to delta S system is, overall delta S system is Q reversible by T, then minus for surrounding Q reversible of system by T, that is equal to 0. So, entropy change or total entropy change, that means entropy change of the system and surroundings together in a reversible process is 0. Now, for the reversible process, let me derive one common equation for entropy change. See, entropy change is delta S overall, this is, and this you can represent is as integration of ds, right? And this is, I am telling about reversible process. So, this is Q reversible, that is del Q reversible by T. Okay. Now, from first law, what we know, that del Q reversible, that is equal to dE plus PdV. What is the condition? Reversible process and only pressure volume work is involved. Okay. So, this is del Q reversible. Fine. Now, that means that ds, or small change of the entropy, that will be is equal to del q reversible by T, and that will be is equal to d plus PdV. PdV, P is the external pressure, dV is the volume change, divided by T. Now we know that dou A by dou T at constant volume, change of internal energy with respect to temperature at constant volume is equal to Cv. Already all these things we have derived. Cv is the molar heat capacity at constant volume. Okay. So therefore dE is equal to Cv dt, that is for 1 mole. So for n mole, dE is equal to nCv dt. This is for n number of moles. Okay, this is one. And now, if our gas is ideal gas, for ideal gas, we know that PV is equal to nRT. Okay, so P is equal to nRT by V. So all these things I'll put it in this equation. So overall entropy change of the system, delta S system, that will be is equal to your integration of ds, and obviously it is from initial, upper limit is S final, and then now this will be is equal to, from this equation I am writing, that is d by t plus p dV by T. Now we'll replace dE by this equation, that is dE is equal to nCv dt. N is constant, considering Cv is constant within the temperature range. So what we can write? nCv, temperature range T1 to T2. Okay, then dt by T plus, this is dV, that's why I have converted pressure in terms of volume. Now here N is constant, R is constant, I can take it outside of the integration. So nR, then V1 to V2, then what is left over? dV. Now nR T dV, okay, nR I have taken outside, T by V, then dV, and this is I have divided by T, no, this is the d plus P dV divided by T. So here it is P dV by T, and this divided by T. Okay, this T. So now this T and T gets cancelled. So what is left over? Left over is, that is your delta S system, that will be is equal to nCv, once again I am writing, that is integration T1 to T2 dt by T plus nR integration of V1 to V2. Okay, now dV by V. So if I integrate these things, then delta S system, that will be is equal to NCV ln T2 by T1. Hope you know the formula. 1 by T, integration of 1 by T dt is log T. Log I am taking base C, that is ln T. So upper limit minus lower limit, ln T2 minus ln T1, so ln T2 by T1. In the similar way it is nR ln V2 by V1. So this is the equation for this entropy change of this system, and we can apply this equation for all the processes depending on the condition. Okay. Now one by one we'll start it. See, first one, entropy change in isothermal reversible process of ideal gas. Okay. So now we'll start. This entropy change of this system, what we can write it is that, means from this equation, that is delta S system is equal to NCV ln T2 by T1 plus nR ln V2 by V1. Right? Now this process is isothermal. Isothermal means temperature constant, that is delta T is equal to 0, or you can write T1 is equal to T2, anything. Okay, that means this part is getting cancelled. So what is the entropy change of the system? Entropy change of the system will be nR ln V2 by V1. Right? So, now entropy change, now I have to find out the entropy change of the surroundings. Right? Now entropy change, say if I write the small change, ds is equal to del Q reversible by T. So from this equation I can write that del Q reversible is equal to T ds. Okay. Now entropy change of the surroundings, that is delta S surroundings, that what I can write, if I want to express in terms of small quantity, so I have to take integration of this integration of del Q reversible, okay, by T. So this will be my integration of del Q reversible by T, and surrounding is releasing heat, so it will be minus if I take outside of the integration side. Okay, so here I am writing in terms of system, but it is negative, so you can write del Q reversible of system by T. Right? So del Q reversible is nothing but the minus integration of T ds of the system by T. So again T gets cancelled. So it is equal to minus integration of entropy change ds of the system. Okay. So this is in terms of small one. Therefore, overall entropy change of surrounding, therefore delta S surroundings, overall if I want to write, that will be minus delta S of, you can write in terms of system, delta S system. Okay, surrounding and system, only difference is system is absorbing heat, so entropy change is positive, same amount, and surrounding is releasing, so entropy change is negative. Okay, so therefore this overall entropy change of system and surrounding, that is delta S total, which is equal to delta S, we call it as universe, that is equal to delta S system plus delta S surroundings, right? Now delta S system, how much? Delta S system just now we have derived, that is plus NR ln V2 by V1, and delta S surrounding is minus delta S system. Just now I have shown you delta S surrounding is minus delta S system. So therefore it is minus NR ln V2 by V1. So that is equal to 0. Okay. Now here one thing I forgot to tell you. See, in the first one when I told you, look at here. In the reversible process, delta S system, that is Q reversible by T, this is not equal to 0. This is not equal to 0, right? Similarly, delta S surrounding is also not equal to 0, but overall delta S of system plus surrounding is 0. So reversible process criteria is delta S universe, that means entropy change of the system plus surrounding is equal to 0. Okay, I am not writing this is 0 and this is 0. This minus this, overall thing is 0. That is the criteria. Now coming to the second one, entropy change in adiabatic reversible process of ideal gas, right? Adiabatic means system is completely insulated. No heat is absorbed by the system from the surrounding, and in other words, surrounding also not releasing any heat. So delta S system, which is equal to Q reversible by T, that is equal to 0 by T. So it is 0. Okay. Similarly, delta S surroundings, that is equal to minus Q reversible. It is releasing same amount of heat. So minus Q reversible of, you can write system divided by T, and so it is just minus sign is there, 0 by T is equal to 0. Okay, minus 0, that means 0. 0 by T is equal to 0. So 0 plus 0 means overall entropy change of the universe will be 0. But you see, it is on adiabatic reversible process. A process is going on. That means when a process is there, that means temperature, pressure, volume is changing. So entropy is also changing. then how come entropy of this system is 0? Okay, but from this formula it is coming 0. The reason is that, see, you know that entropy change of the system, already I have written this one, entropy already I have derived, that is equal to NCV ln T2 by T1 plus NR ln V2 by V1. This already I have derived. Okay. Now here what happened in adiabatic process, so entropy change of the system is due to entropy change of the temperature plus entropy change of the volume or pressure. In case of adiabatic process, what happened? Entropy change of the system due to change in temperature is exactly compensated by the entropy change of the system due to change of volume or pressure. So, entropy change of the system will come as 0. So, in adiabatic process, entropy change of the system due to change in temperature is exactly compensated by entropy change due to change in pressure or volume. So therefore, what we got? That total entropy change, that is delta S total, is equal to delta S system plus delta S surroundings, that is equal to 0 plus 0 is equal to 0. Okay. So, adiabatic reversible process of ideal gas, entropy change is 0. Entropy change of the universe is 0. So, we stop here today, and in the next video I will discuss about the entropy change in the isochoric process for the ideal gas, that means where volume is constant, and then isobaric process where temperature is constant. So, hope you have understood. Thank you.